Everyone. I hope I'm audible.
Good evening, ma'am. Yes, you're audible.
So yes, let's start today's session. If you want to ask something related to last lecture, last session. Okay, as some of you were asking related to the Cauchy-Schwarz inequality, I'll start with that. So we had theorem 10.1. Let V be an inner product space. I hope you all remember the properties of inner product space. Define define a norm on the inner product space in this way, under root of inner product VV. Then we have modulus UV is less than equal to norm U, norm V for every UV in V. And this inequality, this is called Cauchy-Schwarz inequality. Furthermore, we have this equality if and only if these U and V are linearly dependent. By linearly dependent, if you remember, we have done an your linear algebra course. You must have done this. We say two vectors are linearly dependent if there exists some alpha, beta, not all zero. That means both of them cannot be zero together, such that alpha u plus beta v is equal to zero. Now let's look at its proof. It's basic application of the properties of inner product. So now suppose either one of them is zero, then the left hand side of the inequality is inner product of V with zero. And we have seen earlier that this is equal to zero. And the right hand side is norm U, that means norm of zero, norm V. This is again zero. Therefore, we get the inequality trivial. Therefore, we get, let's mark this as star, star. If either, similarly, you can say if V is zero, if either U or V is zero. Now let's look at the case when uh, one of them is non-zero. Now suppose this V is non-zero. U and V both are non-zero. In that case, we define W to be some other vector such that W is equal to U by norm U. Clearly, since U and V are non-zero, norm U and norm V are non-zero, so we can divide. This is basically just the scalar multiplication of vectors by the scalars, one by norm u and one by norm v. So from here we get, by the first property, 0 is less than equal to inner product of WW. This is the first property of the inner product, that inner product with itself is always positive. Now, by definition of by the way we have defined W, this is 1 by norm u times u times u times so next, by the fact that inner product is linear with respect to the first as well as the second component. This is 1 by norm u minus 1 by norm u. Oops. 1 by norm u minus 1 by norm u. Now using the linearity with respect to second component, we'll get this is u square minus uv norm u norm v minus vu norm u norm v plus vv by norm v square. Now, since this in the way we have defined norm, the norm v square is actually inner product of vv. So this is equal to 1. This is also equal to 1. And this is equal to 2 minus 2 times, since we have the symmetry. These both the terms are same. So this is 2 times uv by norm u norm v. Till here, I think it was clear from the proof that was provided. So from here, we get this. Now, since this was greater than equal to 0, from here we get 2 is greater than equal to 2 times no product uv norm u norm v, and
Ma'am,
this is happening. Yes.
are we using the fact that this under root of UV,
Mhm.
the inner product of UV, is a norm here?
Inner product of uv is a norm.
Yes,
No,
are we using this fact?
no, we have defined norm in this way, na?
Okay.
Under root inner product of v with itself. So
Is it
this,
a norm?
yes, it will form a norm. I think it must have been done somewhere. This is how we define norm on an inner product space. If
It's
we
because
have inner product,
in corollary 10.1,
hmm,
in proving that this is a norm, it uses the fact that Cauchy-Schwarz inequality. It uses the fact of Cauchy-Schwarz inequality.
okay, so
So
you
my
are saying
question
that
is, while proving Cauchy-Schwarz inequality, where are we use that it is a norm? If then how this proof are independent?
in the proof of corollary 10.1, where we have used the Cauchy-Schwarz inequality. So don't consider it to be a norm. If we start with just a function, then also till here we have nowhere used the fact that this is a norm. Have we used any property of norm till here? Just this was the definition here.
Okay, then that norm of you that you Um,
Consider it to be some notation.
okay,
Some
okay.
notation.
It is a scalar,
Huh,
isn't it?
huh.
Okay.
This is some function. It is defined such a way any v is mapped to under root inner product of v with v. Okay. We will
Okay,
not use
ma'am.
any property of norm.
Okay, ma'am. Thank you.
Hmm. But yeah, this happens for every uv, uh, which are non-zero. And this implies this inner product of uv is less than equal to uv for every uv non-zero. Since this is happening for every uv non-zero, I can replace v by minus v. So this implies u or u by minus u. This is less than equal to norm u, norm v. Now this will remain positive. The right hand side will remain the same because of the definition. Because the minus this is equal to under root minus v minus v. So by linearity, this minus and this minus will come out. So eventually this will be equal to norm v. Here also we haven't used any property of norm. This is just the property of the function. So from here we get minus uv is less than equal to okay. So this is also happening for every uv non-zero. By first and second, we can write second. So multiplying the second by minus 1, we'll get minus uv. This is less than equal to inner product uv. And by first, this is less than equal to norm u, norm v. Therefore, we get modulus is less than equal to. Is it clear now how we are getting this inequality?
Yes, ma'am. It is clear now.
And the equality part, I hope you can do.
Okay, ma'am.
Next, we'll discuss that example 10.9. So we have the space, consider the space Y to be Bxr, which is the collection of all those functions which are from X to R, and this F is bounded. We have a collection of bounded functions defined on X. Then over this space, we define pointwise addition and pointwise scalar multiplication. Uh, and again, norm to be the supremum mod fx, x belonging to x. We need to show that for the product. Now this fg, this is product, not the composition. Fg is less than equal to f every fg in x. Let f and g belonging to bx are be arbitrary. Then let's denote alpha to be the norm of Fg, which is by definition supremum mod Fgx, x belonging to x. Beta to be norm F, supremum mod Fx, x belonging to x, and gamma to be sup norm of G. These are just some positive real numbers. And we need to show that this alpha is less than equal to beta gamma. So can you try this yourself?
Okay, ma'am, I will try this.
So all you need to use is the fact that alpha is supremum. So for any x, we have fgx. This is just the product. Fx times gx modulus. And we know that we can write it mod fx gx. Now, since mod fx is less than equal to beta and mod gx is less than equal to gamma for every x, so this is, and hence we are done. Is it clear how we are done from here?
Yes, ma'am.
Oh.
It is the property of supremum, isn't it?
Yes, yes. Since this is happening for every x in x, so this inequality will occur for the supremum as well. X gx, this is also less than equal to beta gamma, because beta gamma are two constants. This is just a constant, and on the left hand side we have for every x. So that so the supremum will also satisfy the same inequality. That means alpha is less than equal to beta gamma. Let's move to the exercise problems. Let X be a matrix space with 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 two strongly equivalent matrices. D and D. Show that the sequence Xn converging to X in XD if and only if it converges to X in X D prime. That means in strong convergence, strong equivalence, we have same convergence. So, any idea? Okay, we will start with convergence in one's matrix and then try to see what can be done for the other one. So since D and D prime are strongly equivalent, then we know that there exists some alpha beta. Exists some alpha beta positive such that this alpha times dxy is less than equal to d prime xy. This is less than equal to beta times dxy.
Ma'am,
Okay.
can we do it
Hmm?
by xn converging to x in xd? That means d of x and x is less than epsilon for n greater than equal to capital N.
Hmm.
And then we use the fact of strongly equivalent, that is alpha
Yes.
beta, and change the
Yes,
epsilon accordingly. That
exactly. So let xn converges to x in xd. This implies for epsilon positive, there exists some n naught in n such that dxn x is less than epsilon. We'll change this epsilon accordingly for every n greater than equal to n. Now this d prime x and x, this is less than equal to beta times dx and x by strong equivalence. And we know that dx and x is less than epsilon for all n greater than equal to n naught. So if I take this to be epsilon by beta, get this to be equal to epsilon. And hence d prime x and x, this is strictly less than epsilon for all n greater than equal to n naught. This implies xn converges to x in xd prime. Similarly, you can do the converse part. Next, we will see that this happens even if we have just equivalence. That means we do not, even if we do not have strong convergence, when we have mere, when even if we do not have strong equivalence, that means for the case of mere equivalence, in that case also, the convergence is same. Show that the above holds even if D and D prime are merely equivalent. That means they need not be strongly equivalent. That is, XD and XD prime generate same topology. So eventually they have same open sets. So now we'll try to convert our definition of convergence in terms of some open balls instead of just the distance. Now we'll convert it into open balls because we know that open balls in both the spaces are same. Let xn converges to xn fixed. This implies, by definition, for any delta positive, there exists a stage and not in n such that dxxn, this is strictly less than delta, for every n greater than or equal to n. That means, now since dxxn is less than delta, that means xn of this xn belongs to the ball with respect to matrix D around x with radius delta. So from here we can say that for any delta positive, there exists a stage and not in n such that the elements of the sequence xn belongs to the ball with respect to matrix D around x with radius delta for all n greater than or equal to n. That means if we have a matrix space and this is x, this is ball around x with radius delta. That means after a stage, all the elements of the sequence lie inside this ball. Now, what we want to show that this xn converges to x with respect to the matrix D prime as well. That means we want to show, and this is, by the way, we can write here, this happens if and only if both the definitions are equivalent. Now what we want is that xn converges to xn xd prime. That means xn belongs to all with respect to matrix D prime around x with radius delta or some epsilon. We'll show this for some epsilon for all n greater than or equal to n. This is what we want to show. Now since B D prime x epsilon, let's start with some epsilon. Since B D prime, we'll start with, let epsilon positive be arbitrary. Since B D prime x epsilon, this is an open ball in in x D prime, is open in x D prime. This implies it is open. It is an open set in x D because both the spaces are equivalent. Now, since this is open and x belongs to this set, obviously x belongs to B D prime x epsilon. That means there exists some delta positive such that x belongs to, there exists a ball around x in D because it is open in XD, which is contained in the set which is open. That means BD prime x epsilon. Now, since I hope till here it is clear how this is happening. So we started with an epsilon positive, arbitrary. Now this, considering this open ball, this is an open ball with respect to matrix D prime, and this hence this is open in D prime. Now since D prime and D are equivalent, that means it is an open set in with respect to the matrix D. We do not know whether this is an open ball or not, but still, since it is open in D prime, it will be open in D. So now since this is an open set in D and X is an element in this set, so this X is clearly an interior point with respect to the matrix D. That means there exists a ball with respect to the matrix D, which is contained completely in the open set B D prime. So now, since Xn converges to X in XD, so we started with the convergence in XD, this implies there exists a stage n not in N such that for this delta, Xn belongs to BD X delta for every for every n greater than equal to N naught. That is, Xn belongs to BD X delta. Now, since this BD X delta is contained in BD prime X epsilon for every n greater than equal to N. This is my first. And let's this as star. So this implies Xn belongs to BD prime X epsilon for every n greater than equal to N. Since epsilon positive is arbitrary, we started with some arbitrary epsilon. Arbitrary. This implies for any epsilon positive, there exists some n naught, obviously it depends on epsilon, such that Xn belongs to Bt prime X epsilon for all n greater than equal to N naught, and hence by star Xn converges to X in XD. I would like you to go through this again. And let me know if there is some doubt.
Ma'am, you are not audible.
I'm not saying anything. I was waiting for you.
Oh, okay, okay.
Okay, then let's move to next question. Similarly, we can see that in the case of strong equivalence, the let D and D prime be strongly equivalent. Similarly, I want you to try this converse part also. Here we have shown that xn converges to xn xd implies it converges in xd prime also. Show that exactly similar way you can show that if xn converges to x in xd prime, then it converges in xd. Means let d and d prime be strongly equivalent. Suppose show that the Cauchy sequences in xd and xd prime coincides. So again, using the condition of strong equivalence, we can directly show exactly similar to what we did in the case of convergence. Suppose xn converges to, sorry, xn is Cauchy in xd or in epsilon positive, there exists a not in n such that dxn xn is less than epsilon for all n greater than or equal to n naught. And now since d and d prime are strongly equivalent, we get d prime xn xn. This is less than or equal to some beta times dxn xn. Now this will be less than epsilon if we take epsilon by beta here for all and n greater than or equal to n naught. This implies xn is Cauchy in xd prime. Similarly, you can see the converse part. So for strong convergence, for strong equivalence, Cauchy as well as convergence both are same. For mere equivalence, we have seen that convergent sequences are same, but the problem occurs for the case of Cauchy sequences. That means if two matrices are merely equivalent, in that case, the Cauchy sequences need not be the same. So we have show that if d and d prime are just equivalent, and xn is Cauchy, with respect to the matrix D, it need not be the case that Xn is Cauchy with respect to D prime. So we'll look at some example. So if you remember, in order to see the difference in the case of mere equivalence and strong equivalence, we used a matrix something of the form dxy equals to d prime xy equals to dxy upon 1 plus dxy. In this case, the problem is that this d prime is always bounded. So that can be used here again because we know that in R, the bounded sequences has Cauchy subsequence. So yeah, and with respect to the matrix D prime, any sequence is always bounded. So that will give us some issue. So if I consider X to be R and we define dxy, this is equal to mod X minus Y upon 1 plus mod X minus Y, and d prime xy is just the normal distance, mod X minus Y. Now if I consider the sequence xn equals to n, consider the sequence xn equals to n for every n and n. From here, clearly this is not Cauchy with respect to the D prime matrix, because if it is Cauchy with respect to D prime, you will eventually get that it is convergent or it is bounded in general. Okay. Now this implies D xn xm, this is equal to mod n minus m upon 1 plus mod n minus m. So without loss of generality, let n greater than equal to n. This implies dxn xn. This is equal to n minus m by 1 plus n minus m. This is always less than equal to 1. That means distance between any two, after a stage, distance between any two terms of the sequence is less than equal to 1. So from here, we can clearly see that this xn is bounded. And hence bounded in R, and hence has a convergent subsequence.
Ma'am,
Yes,
it will be bounded after some stage or it will be bounded for every n.
then you can say it for every n also, no? Because before some stage you have finitely many terms. You can take its supremum and you can take the maximum of those finitely many terms. And after that stage, we know that it is bounded. So eventually we can take some upper bound equals to maximum of those finitely many terms and the supremum of the rest of the terms. Suppose m naught. So eventually it turns out to be bounded. The way we used to prove that every convergent sequence is bounded, similar to that. Hence has a convergent subsequence, say xnk. So basically xnk is equal to nk. This is convergent with respect to D matrix. Sorry, this is Cauchy. bounded sequence as a Cauchy subsequence. But if this is convergent with respect to metric D prime also, sorry, if it is Cauchy, now if this define other next another sequence yk will be xn, so that is okay xnk, which is nk, is Cauchy with respect to d prime as well. That means for any epsilon positive, there exists a stage n naught in n such that nk minus nj, this is less than epsilon, for all kj greater than equal to n. This is just the definition of Cauchy. Now, since these are two distinct natural numbers, nk and nj, that's how the sequence was defined. Na? Xn was 1, 2, 3, x1, x2, x3. So nk and nj are two distinct natural numbers. This implies since nk and nj belongs to n, this implies either they both are equal or nk minus nj is greater than equal to 1. Now, for k not equal to j, obviously nk is not equal to nj. This implies for k not equal to j, this nk minus nj, this is strictly this is greater than equal to 1. Now, this contradicts the fact that this is Cauchy, the sequence is Cauchy, because in that case, we can take epsilon to be anything. Taking epsilon strictly less than 1 in equation 1, this happens for every kj greater than equal to n naught and k not equal to j. We get a contradiction. Hence, this sequence is not Cauchy with respect to Cauchy with respect to the matrix. It was Cauchy with respect to D because it was eventually bounded. From there, we got Cauchiness, but it is not it need not be bounded with respect to the Euclidean standard Euclidean metric. The main issue was that here we are getting this is less than equal to 1 always. So next, let's recall previous session question number, last question, where we discussed some equivalent matrices on the product matrix space. So recall question 8 in tutorial 2. So that uh, show that x n y n sequence in this space x cross y is this convergent to xy and x cross y if and only if xn converges to x in x.
Ma'am,
Yes.
every real bounded sequence has a Cauchy subsequence. How?
How?
Yes.
Go back to real analysis 1 course. You must have done something like Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence.
Okay, okay, ma'am.
Okay. Solution. So I think this you can try it yourself. If you remember the matrices that we defined different matrices on this product space, and all three of them were strongly equivalent. So I'll prove this for just one. For the other matrices, you can do yourself. So suppose we have the sequence x and yn converges to xy. This implies for any epsilon positive, there exists a stage such that d max x and yn xy this is strictly less than epsilon for all n greater than equal to n naught. That means dx and yn, which is obviously dx and x. Dx and x, this is less than equal to maximum of dx and x and d prime by n y. This is less than epsilon for all n greater than equal to n naught. Also, similarly, d prime by n y, this is less than equal to maximum, which is strictly less than epsilon for all n greater than equal to n naught. From here, we get dx and x is less than epsilon for every n and n naught, d prime by n y less than epsilon for all n greater than equal to n. Now this implies xn converges to x in xd. Yeah. And this implies yn converges to y in y d prime. Further, since we have seen that in equivalent matrices, the convergence is same. So in that, using that strong equivalence condition, you can see that these, yeah, anyways, that's not needed. All I want to say that instead of this D max, you can consider the other two matrices that we had seen earlier, which are strongly equivalent to D max. So yeah, try its converse part. Conversely, try to show that if xn converges to x and yn converges to y, then x and yn converges to xy in the product space.
Now, without using the strongly equivalent condition, individual, you can also prove that in Euclidean metric or and the third one,
Hmm.
there also this will hold, no?
Without strong equivalence. You're
Yes.
saying that even if we didn't had strong equivalence, we had just equivalence, and x n converges to x, y n converges to y. In that case, you can show that x and y n will converge to x, y. Try.
Okay,
Have you
ma'am.
proved it? So this part actually it's supposed to be done by you. I want you to try this. I think it should be done. Okay, try this. Its converse part. We'll move to next question. Next, formulate the definition of a uniformly continuous map. So, can you tell me the definition of uniform continuity in R space of real numbers?
Given any epsilon greater than 0,
Mhm.
there exists a delta greater than 0, so that whenever d of xy is less than delta, it will
Mm.
implies distance of fx and fy is less than epsilon. And this delta is independent of choice of x and y. It only depends on epsilon.
Depends only on
Epsilon.
epsilon. Good. So here, if the function f was from x to y, this is metric with respect to y, and this is with respect to x. Sorry, this is with respect to y, and this is with respect to x. Definition of uniformly continuous mapping between two metric spaces x and y. Good. So next we'll look at the space of bounded linear functions or the non-linear bounded linear functions. So that if E and F are non-linear spaces, spaces with F being a Banach space, then the space is LEF. This is the space of all bounded linear operators with the connection of all those functions f from E to F. F is a bounded linear function. That means a linear transformation which is continuous as well.
Ma'am, in the above question where you are asking that when we take Euclidean metric or other metric,
Hmm. The
I
converse
proved
part.
that for Euclidean metric without using the strong equivalence.
So you have shown that if xn converges to x with respect to the Euclidean metric. So on x cross y, you were taking
Hmm.
the metric to be dE. So here instead of d max, you were taking dE, and
Yes, ma'am.
you didn't use the fact that it is strongly equivalent to d max. That's what you are saying, no?
Yes.
That can be done.
Okay. Okay.
This I'm saying that I can take d max because all are equivalent. So if you are proving this for dE for d max, both are correct. That's what I was trying to say.
Okay, ma'am. Thank you.
The operator norm is complete. By complete, we mean that every Cauchy sequence is convergent. We will show that if F is a Banach space, so a Banach space is basically a non-linear space which is complete non-linear space. So in that case, LEF, the space of all bounded linear functions defined from E to F, is also complete. Now let's start with a Cauchy sequence. Let Fn be a Cauchy sequence in the space LEF. That means for any epsilon positive, there exists a stage n naught in n such that norm Fn minus Fn. This norm is the operator norm, strictly less than epsilon from all n greater than equal to n. Let's mark this one as equation. So we will be taking the definition. So we have some equivalent definitions for the operator norm. The one that we will be taking is the infimum of all those alpha positives such that this norm Fn minus Fmx is less than equal to alpha times matrix for every x in E. So by the property of infimum, so this is basically infimum over a set. We know that for any epsilon positive or any epsilon for any epsilon positive by the property of infimum, there exists some alpha in this set such that the infimum, which is equal to the norm plus epsilon, is strictly greater than alpha, where alpha is such that it belongs to the set is such that norm Fn minus Fn x, this is less than equal to alpha times norm x for every x in E. Okay, so this implies norm Fn minus Fn x by norm x. This is less than equal to alpha from here. And this alpha, if I write this as this one as third, fourth. Now this is coming by fourth. And this alpha is strictly less than norm Fn minus Fn. This epsilon. This is coming by third. And since we are dividing by norm x, we should take for every x in E minus C. Now, by first, we know that this norm Fn minus Fm is strictly less than epsilon. This is less than epsilon. This epsilon for every n greater than equal to n naught by first. So instead of epsilon, I'll take epsilon by 2 everywhere. 2, epsilon by 2, epsilon by 2. So we get
Ma'am, which is the equation number 4?
equation number 4, this one.
Okay, okay.
This implies norm Fn minus Fnx by norm x. This is strictly less than epsilon for all n m. So this is for n greater than equal to n naught, and for every x in E minus t. This implies for every x in B01 complement, that means for x such that norm x is greater than equal to 1, we get epsilon strictly greater than Fn minus Fn x by norm x. Now, since norm x is greater than equal to 1, 1 upon norm x, this is less than equal to 1. So, this should be greater than. Yeah. Yes. So, do you remember the alternate definition of norm? I think I did some mistake. So, from here, basically, you will get operator norm. If you remember, if you can recall, this is an alternate definition for norm Fn minus Fm. From here, you'll get this to be less than epsilon for all nm greater than equal to n naught. Basically, let me. Yeah, I'll do that proof in next class. So basically, these norms are equivalent. I think it was
Do
an exercise
do we
problem.
use x is x is equal to h of x naught, where x naught
X is equal to
is fixed, h of x naught,
h x naught.
h into x naught, and then we take this to x to 0, x naught is fixed.
Something like this, and taking h tending to 0. Okay, I'll prove that in detail. So basically, it was an
Okay,
exercise problem also. So they are equivalent norms, equivalent definition for the operator norm. So you see, yeah, if you see exercise 10.20 from here. Okay. In next class, I'll prove this part also, that this operator norm, this is equal to supremum norm dx by norm x, x and x minus c. And do this. So from here, eventually, you'll get this Fn is Cauchy, Fnx, sorry. Fnx. Okay. I'm so sorry, there's something wrong. So all we need to show from here is that Fnx is Cauchy. And then use the fact that since Fnx is a sequence in F, which is Banach space, so Cauchy will imply convergent. Yes, Cauchy. For x norm x less than equal to 1, that is when x belongs to, this is happening for every x in E. So when x belongs to B0, 1, we have norm Fn minus Fnx this is less than equal to alpha times norm x. This is coming from equation 3. Sorry, equation 4. It's coming by equation 4. And since norm x is strictly less than 1, this is strictly less than alpha, which is strictly less than norm Fn minus Fm plus epsilon by 2. And this is coming by equation number 12. And this is happening whenever this n and m, this is strictly less than epsilon by 2 plus epsilon by 2 for all n and m greater than equal to n naught. This gives us norm Fn x minus Fm x. This is less than epsilon for all n m greater than equal to n. So from here we get that this Fnx is Cauchy. And similarly, I would like you to try for mod x greater than 1. I don't think it will affect, because this n naught can depend on x. In that case, this n naught will depend on x. This Fnx is Cauchy in F. Similarly, for other x in F. Okay. Now since this F is a Banach space, and Fn x and Fn x is Cauchy in F. This implies Fnx is convergent in F for every x in E. Now define Fx to be that limit at every x, limit n tending to infinity. Since for every x, Fnx is convergent, so that limit is mapped, so the point x is mapped to the limit Fnx. Now we will show that this f will be limit of Fn in terms of operator norm as well. So we claim that this Fn converges to F in the space NEF. That means it converges with respect to the operator norm. So for that, we should firstly have that this F is a bounded linear function. So I'll write it as subclaim. So obviously the limit should be in this space. This F belongs to NEF. Clearly, since each Fn is linear and F is the pointwise limit of a sequence of linear functions, so it will be linear. Clearly, F is linear. Next, we need to show that this F norm Fx is less than equal to some alpha times norm x. And hence we'll get that this F is a bounded linear function.
Ma'am, can you please again how this f will be linear?
Because this F is a pointwise limit of sequence. So if we want to show that something is linear, all we need to show that f alpha x plus beta y is equal to alpha fx plus beta fy. Yeah. And by definition, this is equal to alpha times limit n tending to infinity fx plus beta times limit n tending to infinity fy. That is what we need to show. So our LHS is f alpha x plus beta y. And by definition of f, this is limit n tending to infinity f alpha, sorry, this is fn.
Fn alpha x plus beta y.
So this is fn alpha x plus beta y. Now since each fn is linear, I can split this out. I can write this alpha fn x plus beta fn y. And by the algebra of limits, I can write it as alpha times limit n tending to infinity fn x plus beta times limit n tending to infinity fn y. And this is by definition alpha fx plus beta fy. So therefore, this f is linear. Then we know that if a function is linear and there exists some alpha positive such that norm fx is less than equal to alpha times norm x for every x in E, then we say that f is a bounded linear function. So all we need to show is that such a condition holds. Linearity is clear. This comes from the linearity of the functions and the
Yes,
algebra
ma'am.
of limits. Okay.
Thank you.
So taking epsilon equal to 1, clearly there exists some n, I'll take that n1. There exists some n1 in n such that norm fn minus fm is strictly less than 1 for all n greater than equal to n1. This comes by the Cauchy-Ness. Now, since fn and fm are bounded linear functions, we get this fn minus fmx. This is less than equal to norm fn minus fm times norm x. If you remember, the operator norm also satisfies this condition. Now this will be strictly less than x norm x for every n and m greater than equal to n. Now taking this m tending to infinity, because we know that this is convergent pointwise, taking m tending to infinity, we get norm fn minus fx is strictly less than norm x for every n greater than equal to n. This implies norm fx, this is equal to, I can just add and subtract fn1 x. Now by triangles inequality, this is fx minus fn1x plus fn1. Now this is less than equal to norm x. This is by equation about 4th. So now this one is 5th. So by equation 5th, this is less than equal to norm x plus the operator norm of n1 times norm x. So this is, and since this fn1 belongs to LEF, this is equal to 1 plus norm fn1 times norm x. If I take this to be equal to alpha, because obviously n1 is a constant, 1 and norm fn1 is constant. So this implies norm fx is less than equal to alpha times norm x for every x in. Hence, f is a bounded linear function. Next, all we need to show is that this sequence fn converges to f in the operator norm.
But ma'am, in above, we already showed that Fn converging to F.
That
Is
was
that is
pointwise. That was pointwise.
oh, okay.
We had fn x converges to fx. Then converges to fn L f. And for any x in E, we have norm fn x minus fn x by norm x. This is less than equal to norm fn minus f. And this is coming from the fact that fn minus fm is a bounded linear function. since Fn minus Fm is a bounded limit function, this implies norm Fn minus Fn x is less than or equal to norm Fn minus Fn times norm x. So just dividing it by norm x, taking this from C. Now this is strictly less than epsilon by 2 for every n and m greater than or equal to n naught. Now again taking m tending to infinity, we get norm Fnx minus Fx by norm x. This is strictly less than epsilon by 2 for every n greater than or equal to n naught. This implies epsilon by 2 belongs to the set of all those alpha positive such that Fn minus f x is less than or equal to alpha times norm x. And by the definition of operator norm is infimum of this set S. If I denote this is equal to S, then L epsilon by 2, since every element is greater than or equal to its infimum, so this is greater than or equal to infimum over S, which is equal to the operator norm of Fn minus F.
But ma'am,
Hmm.
we didn't consider x equal to 0.
X
Mm,
equal to 0 will trivially hold, na? See, for x non-zero, this is happening for alpha
yes.
equals to epsilon by 2. And for x equals to 0, the left hand side and right hand side will be 0, na? So any alpha will work, even alpha equals to epsilon by 2 will also work. So
Okay, okay,
I
okay.
can write from here, this implies norm Fn x minus Fm x. This is less than equal to epsilon by 2 times norm x. Fd n greater than equal to n naught, n and n. Okay, this was just n. Because again, yeah, x equals to 0. This happens for every x in E. Now, since this infimum is equal to the operator norm, that means epsilon by 2 is greater than equal to this the norm Fn minus F. And this is happening for every n greater than equal to n. This implies norm Fn minus F is less than equal to epsilon by 2, which is strictly less than epsilon for all n greater than equal to n. Again, since epsilon positive was arbitrary, then positive was arbitrary, we get Fn converges to F. Now, since this norm is the operator norm, this convergence is in NEF. I hope this is clear. How we
Ma'am, can
start.
we say that this is a uniform convergence?
You cannot say if the norm was the sup norm, in that case, that's uniform convergence.
In
This
operator now?
this is what we say the convergence in bounded linear functions.
Okay.
Yeah, because norm is not exactly the same. I hope this is fine. We started, I'll explain it again. We started with the Cauchy sequence in the space of bounded linear functions. Then we showed that this Cauchy will implies pointwise Cauchy, and since the codomain is Banach space, we'll get pointwise convergence. From that pointwise convergence, we have shown that we'll eventually get the operator convergence with respect to the operator norm. Yeah, that's what we have mainly proved. Okay, let's move to the next question. Next, this one is a big question. I don't think we'll be able to finish it today. Whatever I'll be able to do, I'll complete it. Given a matrix space XD, we are going to construct its completion. Completion. And X star. The same argument shows that you can complete a norm vector space normed vector space. We'll see how. Fix some x naught in x. Define function fx from x to r, where fxy is mapped to d by x minus d by x naught. This is happening for every y in x, and we are defining for every x in x, we define a map fx. So the first part says that show that fx is bounded. So by bounded function, we mean the range is bounded. That means we need to show that fxy, this is less than equal to some constant for every y in x. So yes, all we need is the triangles inequality of the matrix. By definition, we have fxy. This is equal to d by x minus d by x naught. I'm saying that this is less than equal to mod dx naught x. Why? Because by triangles inequality d by x, this is less than equal to d by x naught plus d x naught x. So implies d by x minus d by x naught. This is less than equal to dx naught x. Now this upper bound is independent of y. This is happening for every y in x. So I can take this mx to be. So we can remove this modulus also because we know that distance is always positive. we have fxy is less than equal to mx for every y in x. Therefore, fx is bounded. Need not be uniformly bounded, but this is bounded for every x and x. I hope this boundedness is clear. Next, we will see that this fx is continuous.
Is it point-wise bounded?
Pointwise. Not pointwise. Matlab, for a fixed x, fx is a function. This fx is bounded. That bound will obviously depend on x, but yeah, each of fx is bounded. Next, we will show that fx is continuous. Again, each of the function fx is continuous.
filter बन जा तू मेरा.
So, in fact, we'll show that this is uniformly continuous. Let y1, y2 belonging to x be arbitrary. This implies fxy1 minus fxy2. This is equal to, by definition, dy1x minus dy1x naught minus dy2x minus dy2x naught. This is equal to dy1x minus dy2x x minus dy1x naught minus dy2x naught, which is less than equal to mod dy1x minus dy2x plus dy1x naught minus dy2x. Now I'm saying that this is less than equal to dy1 by 2 plus dy1 by 2. Can you tell me how?
I think triangle inequality. No?
So basically, this is
D
dy
of y1x
is
is less than equal to dy1 y2
2
plus y2x.
by 2x. Similarly, dy1 x naught, this is less than equal to, again, dy1 y2 plus dy2 x. So this is 2 times dy1 y2. Therefore, we get fx y1 minus fx y2. This is less than equal to 2 times dy1 y2. Now this will be less than epsilon whenever dy1 by 2, this is less than delta, which is equal to epsilon by 2. Therefore, fx is continuous.
Ma'am, is it equicontinuous also?
For equicontinuity,
Does
this
it
should
depend on
be
point
for every
y1,
x.
y2?
For if it is not depending on y1, y2, that would imply that each fx is uniformly continuous. And for equicontinuity, this should be independent of x as well. Yeah, because epsilon delta, nothing is depending on x. I think it should be equicontinuous also. But yeah,
Independent of x or y1, ma'am, y2 for
see,
equicontinuity?
fx is a function, and when we
Mm,
consider this as a collection, we talk about equicontinuity for a collection of continuous functions. For a function
yes.
fx, we talk about its continuity and uniform continuity. When epsilon delta are independent of the point, in that case, we say, so here epsilon delta, if they are independent of y1 and y2, in that case, we say that the function is uniformly continuous. Now, when we are talking about this collection fx, if in this definition, in this condition, this epsilon is independent of this x as well, in that case we say that this collection is equicontinuous. So I think here, yeah, it is independent of x everywhere, because epsilon
Mm.
delta, delta is exactly equal to epsilon by 2. It is nowhere depending on the point y1, y2, neither on x. So yeah, it should be equicontinuous
Mm.
as well.
Ma'am, what is the difference between point-wise equicontinuous and equicontinuous then?
Pointwise equicontinuous.
Yes.
I haven't heard something like that. Pointwise, because so it done in class? Pointwise
Yes,
equicontinuous.
sir, in his lecture, he said that the
Uh,
choice of delta greater than 0 corresponding to epsilon is independent of function coming from the set of
yeah,
family of.
yeah, exactly. If x here, because the collection is eventually depending on x. In that case, we say that collection is equicontinuous, है ना?
Mm.
Yeah, here actually the collection is fx. That's why I was saying that it is independent of x. And
Mm.
what about pointwise equicontinuity?
Mhm.
I
Sir
think.
has defined that if X be a metric space and Y be a Banach space and F be a family of continuous bounded function from X to Y,
Mm,
then that family is pointwise equicontinuous if for each X belongs to capital X
mm,
and epsilon greater than 0, we can find delta greater than 0
mm,
such that d of xy less than delta implies norm of fx minus fy is less than epsilon for every f belongs to capital F. That is the family.
mm.
And he said that if you could choose a delta independent of point also, then we can say the entire family is equicontinuous.
So delta is independent of the elements
Inde-
x and y in the domain of f. Okay, in that
yes.
case, we say that we have pointwise equicontinuity. Yeah, basically you do not have uniform continuity, no?
Yes, ma'am.
Hmm. Yeah, I haven't read that. Thanks for telling me. So basically, in this case, I think the epsilon delta are completely independent of the points y1, y2. So from there we get uh, equicontinuity,
Yes, here I think it will be equicontinuous.
not just pointwise.
Yes, ma'am. Thank you.
Yeah, from here we get that fx is continuous. Next, we need to show isometry. So what do we mean by isometry? Can you tell me what is isometry?
Isometry is a function from one metric space X to another metric space Y, which preserves the distance
Which
between
preserves the distance. That means the distance remains
of
the same.
yes.
F from X to BCXR. So BCXR is the space of all bounded continuous functions. And Fx, this is equal to Fx, is an isometry. That is, for every x, y, and x, distance between x and y is equal to distance between Fx and Fy. That is, we need to show that this distance between x and y, this is equal to, so we are in operator now. We have bounded continuous function equal to Fx minus Fy, where this norm is the operator now. So let's start. For any z in x, we have Fxz minus Fyz by norm z. This is equal to, now this norm is in this Fx was from x to r. So basically this is modulus. By definition, this is equal to dzx minus dzx naught minus dzy minus dzx naught by norm z. So from here, this dzx and this cancels out. So this is equal to 4dzx minus dzy by norm z. And this is less than equal to dxy by norm z. This happens for every z in x. This implies not fxz minus fyz norm z. This is less than equal to dxy by norm z. on norm z equals to 1 mod fx z minus fy z. This is less than equal to dx. From here, we get that supremum fx z minus fy z whenever norm z equals to 1, this is equal to dx. So now I would like you to think yourself how this supremum will be equal to dxy. And this is a definition of the equivalent form of the operator norm. This will give us fx minus fy operator norm. This is equal to. From here we get that this is an isometry. Okay, so next part is direct. I hope you have done this result that every closed
Ma'am,
yes.
when we are proving that fx is continuous, did we use the norm that is sup norm or simple norm?
Fx is a function from x to r.
It
So
means fx is a member of bounded and continuous function from x to r.
yeah, that is other thing. Now we take this fix x, fix one x, then fx is just one function. We need to show that this is continuous.
Okay, okay
Just
ma'am, thank you.
continuity of one fx.
After this, then we are using that it is a member of BCXR, isn't it? And then we are using the
Yes, yes,
supremum now.
yes, yes.
Okay.
Yeah, for next question, maybe I'll start in next class. Yeah, I would like you to recall this fact that closed subspace of complete space, complete matrix space is complete. Have you done this result in class? I think you should have done.
Yes, ma'am.
Okay, then for next problem, next part, the fourth part of this question, you can directly use this fact to prove the given result. Okay, then we'll continue in next class. Please let me know if you want something else to be done, something related to
Ma'am,
theory.
in example 10.20, how can we show that R square by Q square is path connected mathematically?
Let me see example 10
20.
So in which topic it is?
Path connected and connected.
Is it after Ascoli-Arzela theorem or before that?
Uh, yes, ma'am.
Is it after Ascoli-Arzela theorem?
Mm,
No, I'm not able to.
this is at page number 170.
Yeah, I got it. Example 10
Yes, yes,
point.
after Argela's theorem.
Yeah, now tell me that R2 minus Q
That
is connected.
sir had proved it geometrically. But
So you want,
mathematically,
okay.
how can you
Have you
prove it
tried it?
mathematically?
Have you tried it yourself?
Oh, ma'am.
Maybe we can do this in next class. Till then, you
Mm.
also type how we can do this mathematically. Then I'll explain you in the next tutorial class.
Okay, ma'am.
Okay, okay then we'll meet on next
And
Sunday. Hmm?
ma'am, in definition 10.22, in the completion of norm vector space, when we are considering the family of Cauchy sequences that is on V, that is CV,
Hmm.
how it is non-empty?
Definition 10.22.
Yes, ma'am.
Let V be a norm vector space and CSV denote the collection of all Cauchy sequences in V. We define an equivalence relation on CSV as follows. Xn is related to Yn if and only if the sequence xn minus 1 converges to 0. That this an equivalence relation is an easy check. We define the completion of V to be the set V closure. So what you are saying is,
How this class that is CSV,
hmm,
first we need that it is non-empty, no? How can you say that it is non-empty?
you can always find Cauchy sequence, define constant sequence. Constant sequence is
Acha.
always convergent. It will be Cauchy.
Okay, okay.
The
Oh,
space
thank
of
you, ma'am.
sequences will always be non-empty. Okay.
Okay, ma'am. Thank you so much.